we learned about the binary representations of numbers, particularly large numbers, and looked at how binary representations and modular arithmetic exponentiation can help us to calculate things more efficiently. And now, what is the deal with prime numbers? Here, cryptography relies heavily on our ability to find the large prime numbers and our inability to factor large numbers efficiently. The definition is the integer p is greater than 1 is prime if it is only divisible by 1 and itself. For example, 2, 3, 5, 7, 11s are all primes. And definition, an integer n is composite if there exists an integer a such that a by n and a is greater than 1 less than n. The example 9 is composite because 9 is equal to 3 into 3, because 9 is divisible by 9 and 1 and also by the third number 3. So this is to be considered that 9 is a composite number. Every composite number can be factorized uniquely into the product of prime numbers. This is important. How about a theorem to solidify our fun fact, a fundamental theorem that a fundamental theorem of arithmetic, every integer greater than 1 can be written as a prime or as a unique product of two more primes, where the prime factors are written in order of non-decreasing size. Every integer greater than 1 can be written as a prime or as a unique product of two or more primes. For example, 120, 2 into 2 into 2 into 3 into 5, so 2 to the power 3 into 3 into 5. Here 2 is prime, 3 is prime, 5 is prime. So we can write 120 in the form of 3 prime numbers. Same here, 144, 2 into 2 into 2 into 2 into 3 into 3. Here 2 is 4 times, so 2 to the power 4 into 3 to the power 2. Same here for 360, 2 into 2 into 2 into 3 into 3 into 5, 2 to the power 3 into 3 to the power 2 into 5. So here 2, 3, 5 all are primes. So we can simply arrange any integer greater than 1 into the factors of prime numbers. To test if an integer is prime, we can do trial division. To test if n is prime, loop over list of prime numbers pi and check if pi divides n. If pi doesn't divide n for all primes, then n is prime. Important question, how many primes do we need to check? Answer, only those less than equal to square root of n. Suppose a composite number n equals ab, then a is greater than equal to square root of n. It must be the case that b less than equal to square root of n. So checking the primes less than equal to square root of n is sufficient to find one of these two given numbers a and b. Primes and the GCDs. Check n equals 113 is prime. Solution, note that square root of